found in venom, cancer cells. All right, wide variety of things that you need to be able to defend off, and your ability to fend them off your body defenses is what your immune system immunity is all about. Lack of resistance, susceptibility. You're susceptible to something, trouble with it. So when we talk about how your body defends itself, we talk about different lines of defense that sort of are the barriers and defense mechanisms against them. And our first lines of defenses are things to try to keep them from getting in, with the concept being they can't really hurt you unless they can break through these barriers. So we have all sorts of barriers to prevent entry. We have especially the mucous membrane and all their associated structures, and especially a major one, the cutaneous membrane. Huge one for that. A second line of defense, if things make it through, somehow penetrate through this barrier here, you get a splinter or something, things get through these barriers here, you've got these second lines of defenses, which are non-specific. We'll see that in a minute here. When we say non-specific, it means they're not made for fighting any particular type of pathogens. They are generalist here. So we talk about the cells and the proteins of innate immunity. These are generalists. They are not specific against the specific thing that's fighting you right now. They defend and ward off a wide variety of things. And their major goal is to try to sort of tamp down the infection and activate the third line of defense, the cells and the proteins of the adaptive immunity, which is what the lymphocytes provide. This is your strongest, most focused part of your immune system that will be antigen specific and will have memory. Those are two of the ways that the adaptive immunity will be different than the other types of immunity, is that they will be antigen specific and have memory. And we will see it's the memory cells that are produced in here that give you immunity. So when we look at the differences between them, these innate versus the adaptive one here, well, the innate ones are always there, so there's no lag time. It doesn't take a while for it to develop. They're there just all the time. So there's no lag time. You don't have to wait for this to sort of develop. But it is not antigen specific, as I mentioned. They are reasonably effective against a wide variety of issues. And then the last one, of course, here is that they do not produce memory. There's no memory involved with this. That's different than the specific immunity. The specific immunity is antigen specific and has memory, but there is a lag time. Now I'm going to bring this up right now, and I'll bring this up repeatedly over the course of the next hour. The first time you're exposed to something, you develop what's called a primary, the adaptive response, you develop a primary immune system response, first time. And that has a huge long lag time of really about a week to get it rolling. During which time you're getting sick, because the pathogens aren't just waiting around for you to develop it, all right? The non-specific, adaptive, the innate ones are trying to sort of minimize the damage, minimize the destruction, minimize the infection if they do, but you are still getting sick during that period of time.
So you said the first time your body does what?
The first time you're exposed to a particular antigen, like the first time you come down with polio. Good example, the first time you come down with polio. There is a lag time, as I mentioned, about 7 days just to get it started. But if you survive the primary infection and you do develop memory cells, when you're exposed to the same thing again in the future, your immune system response produces what are called secondary responses. The memory cells provide what? Secondary responses that are lightning fast. They begin to be mobilized within hours, not a week, within hours. And the response, the antibody levels are roughly, you ready for this? The antibody levels in secondary responses is anywhere from 100 to thousands of times more than in primary responses. So much so that it's usually going to be able to overwhelm whatever the causative agent is before you even become symptomatic. Just depends on what particular happened. And that's what we mean when we say that you've developed immunity to that. Now, of course, we mentioned that if you survive the first challenge, all right, then you have this memory cells that will produce these secondary responses that act like lightning. So if, for example, you come down with polio, all right, and you survive the initial, which most people who get polio do, they will survive that initial one, all right, then that person who had polio, all right, now has memory cells. So that person who developed polio before is unlikely to develop polio again. Now the problem is, how long does it take for that primary response to kick in?
A week.
And what happens during that period?
You get sick.
You're getting sick. And for people who come down with the polio virus is attacking cells in the anterior, don't write this shit down. Let's see if you remember this from your 109 days here. I tell you what shit to write down and what shit not to write down. But the polio virus primarily attacks cells in the anterior horn of the spinal cord. The anterior horn of the spinal cord, as every child of 5 or 6 knows, is the part of the spinal cord where your motor neurons, your lower motor neurons are going to be exiting, which is why people who get polio end up paralyzed. Now, will they be immune to polio in the future?
Yes.
Yes, but they're paralyzed, all right? So that's the problem, all right? That's what happens when you let your own good immune system do it. Now, you can avoid that, we will see, by getting, what is that V word? What is that?
Vaccine.
The vaccination. What a vaccination does is it tricks your body into thinking you're developing a primary response. It gives you the same kind of organic molecules that you find on the surface of these bad guys here, the viruses or bacteria, almost all viruses here. And your body will develop a primary response. Will it take your body a good week to develop a primary response against whatever you were just vaccinated against?
Yes.
Do you really have to worry normally about getting sick during that period of time?
Yes.
Yes. No? Yeah.
You are going to get sick.
Well, no, you're not going to have to worry about getting sick from that thing because what they have given you, the vaccination, is not infective, all right? It's dead virus or dead little parts of a virus. So that's why the vaccination is such a nice thing, because you develop a primary response, which means you develop memory cells. But you don't have the same risk that you do if you come down with the real infection, because they are injecting you with dead or attenuated viruses, or in some cases, like the new viruses, the new mRNA viruses, they're just giving you the code to make the bad guys protein spikes or something like this, right? So then your body can defend against them. So in either way, whether you have developed immunity, memory cells, from being exposed to a disease itself or vaccination, You'll still develop memory cells that will give you some level of immunity down the road. Doesn't mean you'll never get sick. It just means that if you do come down with it again in the future, all right, the memory cells are going to go into and be able to produce those secondary responses lightning fast. And in most cases, it will prevent you from being symptomatic. Just depends on what kind of disease it happens to be. And we'll see this again a little bit later, but this is a good start. Okay. So let's take a look at these different sort of barriers here. We start with these surface barriers, and a lot of these you've already covered in 109 because a lot of these surface barriers are going to be associated with your cutaneous membrane. All right? You've got these epithelia that have a lot of tight junctions. You've got ciliated cells sweeping stuff out of your respiratory tract. Glandular secretions like mucus. Mucus is sticky, by the way. Anybody figure that out at this point in your lives? Yeah, mucus is sticky. So we line our respiratory tracts with mucus, for example. The pathogens stick to that. The cilia sweep them up and out, a very effective cleaning mechanism. Saliva, for example, also not only just breaks down things, but saliva contains antimicrobial substances here, tears, sebum from your sebaceous oil glands. Has some antibacterial property here. pH, because most bacteria do not grow well in acidic environments. So when we talk about pH here, we're going to see that most of their secretions and surface barriers tend to be on the acid side. You do not want to have a nice neutral pH on the surface of your skin, for example, because bacteria like that kind of environment here. You don't want a nice neutral environment in the vagina, for example, the same thing, because bacteria, yeast will grow very well in the environment. You want a acidic environment like that, all right? The normal pH of your skin is going to be acidic. The normal pH of the vagina is going to be acidic to try to minimize the growth of pathogens here. And of course, stomach secretions are very acidic. When we get to the digestive tract, we will see that you'll see that the stomach really doesn't do a whole lot of digestion. A lot of people associate the stomach with being really your critical digestive organ. But the truth is, it's a holding tank. It's a holding tank where we're trying to kill as many of the microbes in the food that you ate as we can. Keep in mind that as a species, we've only been cooking food for maybe 100,000 years, maybe a little bit more, how long ago fire was. And so we have to have a lot of mechanisms to prevent you from succumbing to whatever the pathogens might be in the foods that you're eating here. So the acidic environment there is there to kill microbial life. That's primarily what it's there for. And there's a little bit of protein digestion going on in there, but not a whole lot. Most of that digestion is going to go in the small intestine. The protein digestion is helpful because you will remember that proteins are the category of organic compounds that provide functions. They're the functional class. They do the tricks. They're the enzymes, the mechanisms. And so by helping to digest all of these important mechanisms, you also help to keep the pathogens from being able to sort of do some work. So again, we have all of these different sort of surface barriers here to help to keep them from getting in. Again, we have these secretions here. Let's take a little bit more of a look at them here. How the lymphatic and immune system works together. Well, we've already mentioned that most of the cells in your, most white blood cells are not in your bloodstream. Most of your leukocytes, white blood cells, are found within your lymphatic system, especially the star player that we've already talked about, which are, the lymphocytes, the B and the T lymphocytes here. And so the cells of the immune system, they take up residence in these lymphatic tissues and the organs, especially the lymphocytes that will hang out on reticular fibers, any place that they find them. Right? And the lymphatic tissues and organs are going to help to trap the pathogens so that the cells of the immune system can then hopefully dispose of them. So the lymphatic organs then can activate the cells of the immune system by housing the antigen-presenting cells that we've spoken of so far that are required to activate the T cells. And those are going to be the macrophages and the dendritic cells. We've seen those before. We will see those again. So immune system types of cells, let's sort of see. We've already sort of seen some of these cells before. You already know that neutrophils are one of your body's best defense against bacteria. They are bacteria slayers. We will see they do a so-so job by themselves, but we will see they are going to work in conjunction with the antibodies produced by the B cells. I don't know if I mentioned this before, but stop writing for a second. I just want to mention it. Have I already told you that antibodies don't kill? Have I mentioned this before?
The antibodies don't kill?
No.
No. So I guess not.
Is this coming as a shock to anybody here? It's like, why bother with them if they can't kill? They can't kill. They can't. They don't have the ability to kill at all right? So why produce antibodies if they can't kill viruses, if they can't kill bacteria, or they can't do anything? Well, one of the tricks that they have is that once antibodies have attached to the surface of a virus or the surface of a bacteria, it targets them for destruction by the phagocytic cells, especially the neutrophils. Neutrophils themselves are very, very cautious about attacking something that hasn't been targeted by antibodies yet, because they want to be sure that they're not attacking normal body cells. And so they don't do a great job of attacking and killing bacteria just that are floating around by themselves. I'm not sure, should I attack? Maybe not, I don't know. But once your body has mounted a true immune system response and has produced antibodies against that particular bacteria, and now there are antibodies that have attached to the surface, then the neutrophils, they don't ask questions anymore. It's not, should I digest it? Should I do something? They just go after it. Like you see like in a National Geographic special, like a bunch of like hyenas like going after like some poor little antelope kind of thing, like a big, that's what they look like. They just go crazy over it. And so even though antibodies themselves don't lack killing power, they activate the other killers, especially neutrophils. Because neutrophils, there's so many in the blood anyways, they crawl out really easily into the tissues where there might be, some sort of infection there. And once antibodies have entered the picture, then neutrophils finish the job off. And it's not just neutrophils that can do this. The eosinophils actually, you don't have a whole lot of them, but they can actually phagocytize things that have been targeted with antibodies, all right? And eosinophils, as you hopefully remember, are one of your few defenses against parasites, like parasitic worms, for example. They don't do a great job against it, but at least they kind of minimize their danger here. Participation in allergic responses, mast cells and basophils. You had a question?
It was just a comment, like how you said, like when the white blood cells attack
Mm-hmm.
certain viruses. I watched a video on how it looked, and every time I see videos of it, you ever see ants on a piece of food, and when you put your foot against it, they start to sprawl out.
Mm-hmm.
That's literally what it looks like.
Yeah.
It looks like a ton of ants attacking food, and that's all I can think of every time I see it. But in a blink of an eye, it's like the virus is gone.
Yeah, they do. And hopefully it doesn't freak too many people out when they see this here, because they think, oh, white blood cells are nice. And then you see them on the video and they're crawling around all over the place here. It's and it freaks some people out. It's like, oh my God, they're crawling all through my body like little ants or something. Guess what, man? It's good. You want them to do that. Good lymphocytes crawling around, losing amoeboid action. Good white blood cells here. Mast cells and basophils are critical for initiating inflammation. They contain inflammatory chemicals. And we will see that there's a cascade of chemical mediators that trigger inflammation. So there are what we will call top level mediators of inflammation and bottom layer mediators, or the last mediators of inflammation. And histamine falls in that category of being one of the final mediators of inflammation. Which is why if maybe I have an inflamed, some sort of inflamed condition, like nasal inflammation, I might take an antihistamine, an anti-inflammatory, histamine, to block that type of inflammatory response here. So there are other chemicals that are involved in that. Histamine is the most important one. And then we have the antigen-presenting cells that we've sort of spoken on, the macrophages. I'm not going to go into a lot of detail. Have you spoken already about the free versus the fixed macrophages and the other ones here? Is that, so just bottom line here, you remember what, hopefully you remember what a monocyte looks like? If you don't now, hopefully you will by Tuesday. That's a hint. This big, massive sort of cell, big kidney-shaped nucleus in it, largest of all those there. While they are inside the bloodstream, we call them monocytes. But like all white blood cells, they crawl around. And when they crawl out, now we no longer call them a monocyte, we will call them a macrophage. And sometimes the macrophages crawl around and then they slip back into a lymphatic capillary and then travel back through the lymphatic system back into circulation. These are the free ones here. But sometimes they take up permanent residence. When they take up permanent residence, often their shape, their morphology will change, and we give them specialized names. So for example, the one that's mentioned here should be microglia cells. I thought they mentioned microglia. Microglia, remember those from 109? They were a type of neuroglial cell that would be found in the brain or the spinal cord that can help to initiate some sort of immune system response if you get some sort of injury that would involve infection of brain or sort of spinal cord here. There were ones in the skin that were called Langerhans cells. Yeah, maybe not. We'll see the ones in the liver that are called Kupffer cells. The lungs have dust cells. All have the same basic sort of function of being able to present antigens. And I think I tried to touch on before that which type of lymphocytes require the antigen to be presented to them on a silver platter. The B's or the T's?
The T's.
The T's. The T's require that antigen presentation. Here, do something with this. And they obtain it sort of slightly different, it sort of seems here. I mentioned macrophages seem to obtain them more by phagocytosis. The dendritic cells tend to do it more by pinocytosis, cell drinking. So in either way, they've got all the bases covered about being able to take in antigens, foreign bacteria, viruses from the environment, chew them up, and present them on the surface to activate which cells? I'll do this again. To activate which cells?
T cells.
The T cells. See how I do that with my hands? To activate the
T
cells. Very good. Other cell types here. NK cells. NK cells technically were a type of lymphocyte, but they work very different than the other types of lymphocytes here. They are considered part of your non-specific defenses. The true lymphocytes, the B's and the T's, they have their receptors that make them immunocompetent. Remember that from our last exciting class? Being immunocompetent, having that receptor. Mm-hmm. So the B's and the T's, once they get activated, they're looking for things that are out of place. They're looking for things that are foreign. That's their job. If they find the one foreign thing that they recognize, that's when they attack it, all right? Not so much the NK cells. They don't look for things that are foreign. They look to make sure that the cells have the right number of normal surface proteins. They're not looking for abnormal, they're looking for what? Normal. Because cells that are infected with viruses often stop producing the normal surface antigens. And cancer cells also do that. When they go rogue like that, they stop producing the normal ones. And these are the kind of things that the NK cells tend to be very good at picking up and destroying. Not things that have a foreign thing, but things that don't have the right number of normal things on their surface here. So when it says destruction of plasma membrane containing abnormal antigens, it means it's not having the correct number of right ones here. Cytotoxic and helper T cells here. There are multiple types of T cells. Really, just one big group of B cells. Let's do B cells here. When the B cells become activated, they differentiate into this massively huge antibody factory that we call a plasma cell. And for the rest of its life, it will just keep churning out massive quantities of antibodies that will provide antibody-mediated immunity. T cells, this is a nice little summary, is a family of compounds that have more of a direct cell attack response, or they will moderate the immune system response. There are ones that are called helper T cells, and we'll see why it's important later to find out they have the CD4 marker on them. The helper T cells are responsible for ramping up all aspects of an immune system response. That's the job of the helper T cell, to ramp up all aspects of that by secreting chemical mediators, cytokines, that will ramp up both B and T cell responses that stimulate cell-mediated and antibody-mediated ones here. So without the helper T cell, we can't ramp up a response. So just a quick heads up about how that works. Remember the other day I was drawing the lymphocytes on the board over there? What did I call the one I drew? Sue, I think, was the one I drew there.
Her name was Susan, but she likes Sue.
Sue.
Thank you, exactly right, because we don't want to disrespect her. Right? Sue is the one who recognized what the deadly triangle virus, correct?
Yes.
So if you come down all of a sudden exposed with the deadly triangle virus, who's going to defend you? Who are you going to call on?
Sue.
What was her name?
Sue.
Susan, yeah, because she's the one that can recognize it and fight it off, right? We're talking about what's happening in a primary immune system response. The first time you've been exposed to something, all right? Now, is one cell, poor little Sue, she gonna be able to fight off a whole army of bacteria viruses by herself?
No.
No, not gonna happen. But once she's first been activated, she's no longer naive, she's been exposed to her particular antigen, all right? She's gonna now get feedback from our friend, the helper T cell, to start growing massively rapidly. So she's gonna grow at an unbelievable rate to divide to become 2 cells. 2 copies of who?
Sue.
Susan, both copies of which can recognize the deadly triangle virus. The 2 then divide to become 4. The 4 divide to become 8,
16,
16.
30.
It's called math. All right. Until a week later, now you've got millions of copies of who?
Sue.
Of Sue, who hopefully can fight off this infection. But it takes a good week, really, to ramp up that primary response, which is why you're getting sick during that period of time. But if you survive it, then we'll see how the memory cells will come into play. But we can't ramp up that response without the assistance of which cells? The helper T cell. The helper T cell is required to what they call clonal selection. We'll see that term later on, to ramp up that army.
Can I ask a question? It might be dumb. So like people that had COVID, right? They had COVID before the vaccine,
Yes.
How did they make those people get it if they fought it and they beat the virus? I know it started having other different types of COVID, like different strains started coming out, but when it was just known as just that one strand, why did they make people tell them you get vaccinated?
Okay, so there's a couple things. There's a lot going on here. We've got to unpack a lot here. So let me start to unpack a little bit. When we say that you develop that Sue can recognize this particular antigen,
Right.
what Sue actually was recognizing was an antigenic determinant. What the heck is that? An antigenic determinant. I'm going to show you a picture. Let's see. Not working what I want it to. Try it again. And why is my keyboard not working?
Is the keyboard on?
Hmm?
Is the keyboard on? Is it Bluetooth? Is there a switch?
I don't think, because my mouse is working fine here. I can do this on the board here. Do I have a keyboard here? Let's see if
The pen, Professor. The pen.
This pen?
No, the one, is that the pen right there?
Mm-hmm.
You think this one will work? You may be wondering to yourselves right now, how this man ever got a job here?
No.
Let me see if there's something. There has to be a better way than this here.
Because if you go for a gun to the monitor.
Let's see, on-screen keyboard. Show touch keyboard, I should say.
It's the keyboard's next to the clock.
Mm-hmm.
Press the search bar first.
Is this working now?
No,
Yeah,
there's
you have to,
something.
yeah.
Ah.
Yay.
All right. So should do this. Here's an antigen here, like our deadly triangle virus. But every antigen has actually, which are generally relatively large sort of organic molecules, have different regions which are foreign. So it's not just one thing, it has different regions that are foreign that can be recognized by different lymphocytes. Each slightly different sort of region that a lymphocyte could recognize as foreign and mount a response against it would be referred to as an antigenic determinant. So most antigens, like a swine flu or coronavirus like COVID, have multiple antigenic determinants on them, meaning that not just one type of lymphocyte like SU would be activated, but several. There could be like 3 different types of lymphocytes that could be activated against this particular virus, all right? Each that would undergo that primary response. Now, when you get sick, something the first time, all right, when your body mounts an immune system response against it, there's no way of knowing how many different types of your lymphocytes actually got activated, because they do have these multiple antigenic determinants on it. For all we know, it might have just been one, which means that you're only going to be able to mount a response against one of those different types of antigenic determinants on it here. When they cook up a cocktail of a vaccine, like the mRNA ones, they're doing enough of them so that you're probably going to be activating at least maybe 3 or even 4 different types of antigenic determinants, which means that your immune system response to the vaccine is going to be much stronger than it might be if you're just coming down with a normal infection. So that's why getting repeated vaccinations and boosters can be happy because every time you do it, there's a chance that you might be activating another set of lymphocytes against a different antigenic determinant, which is why even if you have come down with COVID before and have survived it, then it's still a good idea to get a booster, to get a vaccination, because you will be even more protected than your initial response would be. And I don't know if that's what you were kind of asking or whatever that is. The most important thing about the difference is that both getting sick with something and getting vaccinated produce memory cells that give you quote unquote immunity. The difference between them is what's happening in between. In other words, when you get sick with something naturally, you might not survive it. And if you do survive it, there's a lot of long-term scar damage and issues to other tissues here, right? Yes, like polio, the example, I should have stuck with that. The polio, yeah, you survived polio without having to get vaccination, but like this, but now you're in an iron lung for the rest of your life, all right? But good for you without having to get a vaccination. Now you just have people feeding you in a tube the rest of your life here. So that's the big thing about why it would be important to get a vaccine against something like pertussis, against whooping cough, for example, all right? Instead of just letting your child get it and develop immunity. Have people heard, if you've heard somebody who has whooping cough, you never forget that sound. And all right, and if parents have your children with whooping cough, it's a horrible thing to have to hear your child like that here. That's just one example of something you want to get vaccinated against. Okay, so that was the whole idea behind antigenic determinants here. Okay. So the helper T cells we will see are the ones that will ramp up both B and T cell responses required for mounting up. What would happen to your ability, quick question, what would happen to your ability to mount an immune system response if some agent were to come out and kill off your population of helper T cells? What would that do to your ability to fight off an infection?
Decrease.
What would happen to your ability to fight infection if some kind of agent were to knock out your population of helper T cells?
What would happen? Not enough.
Would you be able to mount enough of an immune system response?
No.
Would you succumb to things that normally your body would probably easily be able to defend against?
Mm-hmm.
Is there such an agent like that out there now? HIV! What? Somebody mentioned HIV. This is what the HIV virus that causes AIDS does. People have forgotten about AIDS now. It used to be front page news, but now it's all coronavirus.
Right.
And now because we have so many effective treatments for HIV, that people with HIV infection are living almost normal lives as long as they're getting their treatment. But the reason that people would die from that is because without treatment, the virus itself attacks and kills off what population of cells?
Helper T cells.
The helper T cells. Without the helper T cells, now you are immunocompromised because you can't mount either a fully effective B or effective T cell response because of that. All right, moving. So we'll see more about the cytotoxic T cells with the CD8 marker. They are the only T cells that can kill directly. They are a type of T cell that actually can kill directly.
Which one?
The cytotoxic T cells.
Can't kill directly.
Kill the virus?
And this is a good time to mention the two most important killing mechanisms that we see over and over and over again before. One important killing mechanism is death by phagocytosis. And that was one thing we mentioned that antibodies will do to make neutrophils kill, because neutrophils then will engulf them by phagocytosis, digest them inside. So phagocytosis, death by phagocytosis, and then internal digestion by that phagocytic cell. That's one important killing mechanism. The second one is death by lysis, Lysis. You have a lot of different types of killing mechanisms that try to kill by poking holes in whatever their foreign targets are, and then making them explode, basically. You poke holes in them, and then they explode. Because if you no longer have an intact cell membrane, you are not long for this world. And there are many different ways that we can poke holes in things to cause death by lysis. Now, would this work against viruses? No, because they don't have membranes, they're not made up of cells. But death by lysis works very well against bacteria. Kill them, poke holes in them, break them open. There's also other regulatory you will see when we get to that section. Do you remember positive feedback versus negative feedback? In positive feedback, the initial response gets ramped up, right? Gets bigger and bigger and bigger. And one good example is the way that the helper T cells work, all right? By ramping up that immune system response, because once that one activated lymphocyte, like Sue, not Susan, like Sue over there was activated, all right? The helper T cells are these chemicals that allow them to ramp up a response. So where the 2 becomes 4, 4 becomes 8, 16 ramps up, right? And it was the same with all types of positive feedbacks that ramp up like that have one danger involved, and that is that they can spiral out of control. Any kind of positive feedback, if you keep accentuating, it can just spiral out of control. Positive feedback mechanisms need some sort of shut-off mechanism to stop them from going on indefinitely. And you might have seen, you probably did, if you did positive feedback, did you do labor contractions with positive feedback? That's a common way that we teach positive feedback, because labor is done under positive feedback. Where the hormone, a hormone oxytocin is released in response to stretch on the uterine wall, especially down by the cervix, all right? And so the more it's stretched, all right, the more you release oxytocin, it makes the next contraction stronger, pushes the kid's head down even more, causing you to release even more what hormone? Oxytocin, making the next contraction what? Stronger, pushing the kid's head down even further, causing you to release even more what hormone? Oxytocin, all right? And so as you progress through labor, the contractions get stronger and stronger, and the interval between them gets shorter and shorter, up through physiological levels, right? You can only do it so much, right? But you need a cutoff mechanism, hopefully, here, right? What's the cutoff mechanism there? Birth, right. Squirt that baby out. Boom, no more stretch on the uterine wall. That cuts out. You know what? My Aunt Carol squirted her kids out like watermelon seeds. Seriously, none of them made it to the hospital. They were all delivered in transit. She had like these 15, 20-minute labors. Like, oh, I'm in labor, I'm on water breath. There's the baby. Where's the baby? And I don't know how to say this nicely. All the other women in my family hated her for that reason. Right. Oh, poor Aunt Carol had to suffer 22 minutes for this labor here. Oh, where's that world's little smallest violin for poor Aunt Carol? Why am I mentioning this? Well, we also don't want the immune system response to spiral out of control. We want to be able to bring it down once you have fought the good fight. And that's what there's other population of regulatory cells here that suppress factors that would inhibit the immune system response after hopefully you have fought off the infection. So we have some types of T cells that ramp up the immune system response. All right. When you were first coming down with that, other regulatory suppressor ones that will help to bring it back down after you've hopefully fought the infection. And then of course you also have one that can kill themselves, which are the cytotoxic T cells. They can kill directly. Notice for memory cells it says T and B because both the T and the B cells, when they are involved in the initial fight, will produce these memory cells that give you immunity. You've got antibody mediated by the Bs, you've got cell mediated by the T cells, and that's the ones that are going to give you immunity here. So let's take a look at these in a little more detail here. This is going to be a little bit of a tricky one here. Complement. Complement is a part of our non-specific innate immunity here. So this is not a B cell response or a T cell response. Complements are a family of proteins that are one of your better mechanisms as a weapon against bacteria or other cells. Made by the liver. So there's multiple proteins involved in this complex that are called complement proteins. And we all abbreviate them with the C. So when you come across something like C5b, the C is standing for complement C3b. C3 is going to be the critical piece. So here's how it works. And then write it down after I tell you how it works. The key goal is that we want to be able to insert these complement proteins into a target membrane. Now, once I get the first critical piece into our target membrane, then like dominoes, you get click, 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 a bunch of other pieces will click into place around it that will form a hole. That will form a pore, if you will. And if you get enough of these, what they will call a membrane attack complex. Do I have MAC down here? Where's my membrane attack complex here? Should be here. Okay, they're showing it here in the bacteria, my membrane attack complex. You can see, but I've got one piece in, then all the other ones click in place. And if you get enough of them clicked in place here, these membrane attack complexes, you poke enough holes in it, then you get death by lysis. Death by lysis. Then it explodes. So the key thing is then, how can we use these complement proteins to kill bacteria? Well, far and away, the most important way that we get that piece inserted, and we refer to that process as fixing. We want to fix complement. When you say we want to fix complement, that means we want to insert it into its target membrane to cause it to die by lysis. So far and away, the most important way to do that, what they call the classical pathway, is that it will be fixed by antibodies. Remember I said before that antibodies by themselves have never killed anything? Lack the ability to kill? But one important thing that antibodies did is once antibodies were attached to something, it targeted them for destruction by the phagocytic cells. We refer to that phenomena of attracting phagocytic cells and making them go into like kill mode as opsonization. Opsonization is making it, I guess, visible to the phagocytic cells, making the phagocytic cells go crazy. Are antibodies by themselves an important opsonin? Yes. because they will promote that process of phagocytosis by the neutrophils, by the other phagocytic cells here. But another thing that antibodies do is that the antibodies have a little location near the surface of the cell that will fix complement. So antibodies that attach to bacteria can cause the destruction of that bacteria in two ways. One is simply by themselves, they're going to attract phagocytic cells, and then the phagocytic cells can digest them. But the other way that they do it is that once you have an antibody attached to that, it will fix complement. And then as you fix complement, you're going to cause death by lysis. And you sort of see the bacteria. Isn't that a good picture? You see the bacteria exploding. So this far and away is the most important, the most common way that you can fix complement. So the complement is an effective mechanism against cellular pathogens because it's going to have to poke holes in a cell membrane. Would complement work against viruses?
No.
No, because they're not made up of cells. But it's extremely effective against bacteria. Now there is another alternate pathway that, coincidentally enough, they just call the alternative pathway, which allows complement to be fixed by organic compounds in the bacterial cell walls themselves. And I'm not going to go into a lot of detail about this. It's not as effective, right? Not as rapid, which is why you really need to have the antibodies there to really do the work. But these other pathways here, lectin alternative pathways, both of them have the ability potentially to fix complement. Once you get that first piece in place, C3, it actually, C3 splits into two parts. I don't want to go into detail. C3, the B is the part that actually fixes the complement. The other part of it that breaks off from it, they call C3A, starts to trigger inflammation. And inflammation also an important defense here. So that's why they're talking about it with C3A here. It's going to enhance the inflammatory response here. It's showing enhanced phagocytosis due to the opsonization here. So complement, effective chemical messenger. Cytokines. Cytokines is sort of a family of immune system hormones. That's what you should think of when you think of that term cytokine. So I'll spend 15 seconds, probably longer than that. Little background story is all right, let me just do it this way here. We had mentioned that inflammation involves several different sort of steps of mediators, all right? You've got bottom level mediators which is the most important bottom level one that you'll be responsible for, histamine. But the most probably important top level mediator that often starts the ball rolling is this one that's called tumor necrosis factor, TNF. Now they discovered this, I'll mention this. They discovered this relatively recent discovery, I think back in the 80s, which is relatively recent here. A lot of you weren't born by that time here, nonetheless, still in terms of history recent. So if you come down with blood poisoning, something they call it there sepsis, which is when you basically have a blood infection here. It's often a fatal, very nasty condition here. Has a very high mortality rate if you're septic. It causes you to go into shock, septic shock. After your septic shock, then you're dead. And there was a doctor who was treating patients who had cancer, and was just, as a good doctor was, sort of attentive, all right? And one of his cancer patients also came down with sepsis, septic shock. Now, if you know people who are going to be treated by cancer, that's hard enough on the body. The cancer itself is hard enough. The treatments that you're seeing, the surgery, whatever, like, is hard enough on the body. And if you're going to add insult to injury on top of that, now you've got sepsis. Now you've got septic shock on top of that. All right. Imagine septic shock. Imagine your worst flu that you've ever had. All right. And now multiply that by like 10. And that's what this sort of feels like here, that kind of thing. It is not pretty. And very few people sort of survive it. However, this physician noticed that this particular patient who actually had sepsis, got out of the hospital, survived it. All right, that's great. He survived this bout of septic shock. Then he went to sort of start the treatment, and lo and behold, his particular tumor had pretty much completely disappeared. Completely sort of vanished. There was only little remnants of that tumor left. It's like, wow, this is unusual. You survived this septic shock, and wow, your tumor also basically sort of disappeared. Wow, that's interesting. And this physician, being curious, wanted to see if this was just an anomaly or if he knew other colleagues that had similar experiences. So he put word out there to his other colleagues in oncology. Everybody knows what oncology deals with, right? Oncology, cancer, right? Mm-hmm. So to other oncologists to say, do you know of other patients who have had something similar to this? And sure enough, other stories started to show up about, yes, I've had this patient here who had this type of cancer, this one here who had septic shock and recovered, lived to tell the tale, whose tumors actually almost completely disappeared or vanished, or almost really atrophied severely. So started to do some research and found out that there was a chemical that's released that mediates septic shock that also had this ability to kill these particular types of tumors. And they named this chemical compound tumor necrosis factor. And for a while, when they first discovered this, they thought, oh, wow, this is going to be, we found a naturally occurring chemical that kills cancers, or at least specific types of cancers. And so initially there was a lot of research saying, well, maybe we can find a way to use what we know about this to cure cancer. So for a decade, they did some work on that to try to find a way to use this to treat cancers, never successfully, because the TNF that they would give to do that makes you so sick as a dog, all right, with these horrible flu-like symptoms, that often the treatment was actually worse than the cancer. A lot of people would not sort of survive that anyways. But in doing this, and doing their research, they found out the role that TNF plays in inflammation as a top-level mediator of inflammation. And as it turns out, there are a lot of conditions that are cause people a lot of grief that are caused by inflammation. You have inflammatory bowel disease, all right, or some inflammatory types of arthritis, for example, like a psoriatic arthritis, and they discover that they can sort of cure these kind of, or treat these things by blocking the actions of TNF. So nowadays, you will see, you can't swing a cat without seeing a commercial for something like Enbrel or other things like that are drugs that block the actions of tumor necrosis factor. And this category of drugs that block these TNF blockers have become like the most sort of widely prescribed. Well, they make a lot of money for the pharmaceuticals, I can tell you that much right now. For treating things like psoriatic arthritis, for treating Crohn's disease, irritable bowel disease, a lot of these inflammatory conditions, rheumatoid arthritis, can now be treated with these TNF blockers. So even though the initial hope of finding TNF that might be a way of curing cancer, even though that turned out to be a complete bust, so far at least, there was, a silver lining to that, in that we found out that we can block it and cure and at least treat. We can't cure these diseases. We don't cure psoriatic arthritis. We don't cure irritable bowel disease, but we can treat it and prevent it from causing symptoms by taking drugs like Enbrel. Oh my God, why am I blanking on the other TNF? They're all over the place. And again, one reason, do you understand why the pharmaceutical industries push drugs like this so much? Because there's not a whole lot of money as a rule in cures for disease. I know I'm gonna sound like I'm very, pessimistic here, but there's just not a lot of whole money for a pharmaceutical company to develop a drug that you're gonna take once, cure your disease, and that'll be it. Where do they make their money?
Longer treatment.
They don't cure. They give you something so it could help with it could help you, but it's not going to cure you, so you can keep buying the drugs.
Yeah.
Oh, so you can keep buying it for how long?
Never long it takes.
Until you die.
For the rest.
Oh,
For the rest of your life. That's where the coin is, people. All right?
That's probably a cure for cancer. The chemo's more expensive.
It's like the most,
That's right.
I'm pretty sure there's a cure for cancer. It's been.
There are some cancers that have been treated. A lot of the research that is more the curative, the stuff I think is done are the ones that are where the research is done by medical colleges and university, because they don't have that same profit driven, profit margin driving like a private pharmaceutical company would have. The private pharmaceutical companies, they're the ones who are primarily focused on things that you're going to take for the rest of your life. Primarily for that. Where university research areas, they're probably the ones that are more involved in finding cures. All right, that's my little soapbox issue for the day. I'm going to be a one soapbox issue in here. All right, so tumor necrosis does induce these flu-like symptoms of fevers, chills, aches. There's another cytokine called Interleukin-1 that's a lot like tumor necrosis factor. Tumor necrosis factor is like Interleukin-1 on steroids. Just a lot of things that Interleukin-1 does, tumor necrosis factor does much more than that. But again, it's a top-level mediator of inflammation, and it's primarily secreted by activated macrophages, our important helper cell here. It releases these chemicals, it attracts other phagocytic cells to the area. That's how it ends up killing the cancers, by attracting the other phagocytic cells to the area here. This other group here, we'll have time to talk about interferons. Interferons are activated by almost all of these types of activated cells. And interferons are one of your best antiviral weapons. When you think interferons, you think about a weapon against what? Viruses. Now, what interferons are produced by cells, groups of cells, that have been infected by viruses. When some cells have been infected by viruses, it triggers them to end up releasing these antiviral proteins that inhibit viral replication in the area that they're being released, in the neighbors, the cells in the neighborhood. Now, the cell that's been infected and releasing interferon, the interferon's not going to help it. It's a goner. It's not long for this world. But in a very altruistic action, it will sacrifice its own cellular life to save the life of what? The other cells. The other cells by releasing what? Interferons. The interferons help to at least minimize the growth of at least some types of viruses. So there are different types of interferons. It is a cure for the common cold. The problem is at high levels it can do damage to your liver. But they used to, I know they used to like take interferons up into space once they discovered this. And they'd go up on the shuttles and the space station. So that if somebody did bring something up and came down with them, you can at least cure it relatively quickly. And interleukins. Great name, interleukins. Interleukin, have we had this conversation before, interleukins?
No.
The name itself, interleukin, tells you that these are chemicals that are released from one white blood cell, primarily to communicate with other white blood cells. Because the name itself, interleukin, tells you it's what? Between white blood cells, between the leukocytes here. And these interleukins do a wide variety of things. One thing that they do, it's the primary thing that causes fever, interleukin 1. It also stimulates production of white blood cells, especially neutrophils. And we will see them in more detail later. How much time we have? Our last thing we're really going to have a chance to talk about much, I think, is going to be a little bit more about inflammation. Because inflammation, as we touched on last time, is a knee-jerk response to tissue trauma. Almost every tissue in your body can undergo inflammation, with only a very few exceptions to that rule. Cartilage cannot undergo inflammation because it's avascular. And inflammation sets in motion a cascade of events that eventually lead to healing. Inflammation activates a cascade of events that eventually lead to what?
Healing.
Healing. Which means that you generally will not get healing of a tissue unless there's some small degree of inflammation. That's why your body just does it automatically. It sets in motion this cascade of events that ultimately lead to healing. Now, we will talk about the difference between acute inflammation, that's short-term, versus chronic inflammation, which would be long-term, ongoing. There are different chemical mediators that go on. Generally, as a rule, as a healthcare clinician, most of the inflammation that you're going to be trying to suppress in your patients is going to be chronic inflammation, like in tendinitis, for example, or some other type of inflammatory condition. Will there be times that you need to get rid of acute inflammation, like airway inflammation? Oh, yes. All right? You don't have time to wait for airway inflammation to go down by itself. That's an acute problem like this. You need to sort of to restore airflow, all right, by getting rid of that inflammation. But I'll mention this, for example. I mentioned cartilage is avascular, so cartilage does not undergo inflammation. What does that tell you about cartilage's ability to heal?
It doesn't.
It doesn't really. And that's a problem. That's what happens in some types of arthritis where the cartilage gets damaged. It's not going to undergo inflammation. It's not going to heal. And really all they can do, if you've got like some joint damage, maybe, is they'll go in there and try to clean up the damaged cartilage as best they can. All right? But there's no real repair that's going to go on with that. So it's a response to almost any kind of trauma. Trauma, bacteria, viruses, toxins, heat, chemicals. And this series of events will isolate the damaged area, help to clean up the damaged components here, recruit cells, and eventually again lead to the repair process. So we've got different stages. The first stage are the release of these mediators here, that are going to be involved in triggering the cardinal signs of inflammation, which I can almost guarantee you're going to need to know for the next lecture test. The 4 cardinal signs of inflammation are redness, swelling, that's the edema, pain, and warmth or heat. And most of these are caused directly by histamine, the final mediator.
You said all four of them are caused by histamine?
Right, most of these are caused. The pain, not as much. Pain is more like the bradykinin. Bradykinins are like pain in a bottle. Ugh. You don't want bradykinin. But histamine makes the local blood vessels, the local arterioles and the capillaries become way more permeable. It opens up blood flow, makes them more permeable. Excuse me. So as I increase blood flow and make the blood vessels more permeable, follow me with this. If I open up the blood vessel, all right, is that going to change the color of that inflamed tissue as I increase blood supply to that?
Yes.
What color is it going to make it with all that additional blood flow? Red. So the redness is caused by the fact that we have increased blood flow to that area because of what chemical mediator? Histamine. The histamine, we've said, also makes the capillaries more permeable, so we get a lot more fluid leaking out, causing the edema. The increased blood flow, since blood is warmer than body temperature, also caused it to be warm to the touch. Sometimes the additional swelling and edema can cause pain, but it's usually the other mediators like bradykinin that's released that's really be more involved in pain here. But one thing that's going to happen, we will see, is that as we make these blood capillaries more permeable, then clotting proteins can begin to leak out that are normally trapped inside of a capillary. Did everybody catch that? Clotting proteins. Will some of those clotting factors come in contact with tissue factor?
Yes.
Tissue factor. Tissue factor. Will that initiate a response?
I'm lost.
Yes.
Oh, you hate when I do this, don't I? Okay. Okay. When we talk about how we get coagulation occurring, we talk about two different pathways that led to factor 10. Factor 10 brought us to our common pathway, where we ended up with prothrombin being converted into thrombin that then converted fibrinogen into fibrin. I know you've erased that so you have room for new material. I understand that, okay. But the only reason I mentioned this is that we're activating that extrinsic pathway when we do this, which means that we're going to form a fibrin web in this inflamed area. Now, can that stop maybe some pathogens from spreading if that's what's causing the inflammation? Yes.
Yes.
And that's sort of the beauty of that phenomena, is that we end up with a fibrin web, all right, in that inflamed area to hopefully trap any kind of pathogens that might have been causing it. And eventually we'll need to break down that fibrin web with tissue plasmin activator. But we've got our inflammatory mediators that are mentioned here. And that's going to trigger the phagocytes, especially neutrophils. Anytime that you see an inflamed area here, there's going to be massive infiltration of neutrophils. You see it really, histology, you see it in the slides really easily. If you take a slide from an inflamed tissue, you just see massive numbers of neutrophils in that area here. They just come running, all right? Now, they're not the first one necessarily there. We also have local macrophages. They're the ones that get initially activated. Neutrophils via chemotaxis. Neutrophils will phagocytize a pathogen, then they die in the process. Sort of a suicide run for them. But again, they only last like half a day anyway, so is it much of a loss if they die?
No.
Yeah, they didn't have long to live anyways, right? So it's like, what's the big loss? It's like if you accidentally like run over like a 90-year-old lady on the road or something, it's like, well, What, she had like a day or two to go? It's like, what's the big, is that just me? Is that wrong?
Definitely you.
Is that like so wrong? Am I like so fired? Okay. So, I apologize for that. That was so wrong. But the neutrophils, they're basically one and done. They release bleaching agents, basically. These oxygen-free radicals that will kill them, and they get killed in the process by the bleaching agents they release, all right? Now, the monocytes can actually live to kill another day. They're longer lived, they're more aggressive, they can kill multiple ones at a time here. And this is trying to show what's happening during this. So here we have our injury. Oh, we've got a splinter. I hate when that happens. It's made it through the epidermis into the dermis here. You can see the damaged cells here, mast cells, which are one of the things that are going to be triggering the inflammation. They've got all these little chemicals filled with chemical mediators, especially which one that begins with the letter H?
Histamine.
Histamine. So we have this histamine here, these mediators that are going to make the capillaries start to become what? Permeable and open up. So we got all this protein-rich fluid coming out here, all right? All this swelling coming out here. The redness and the heat because of the vasodilation, the arterioles here. Pain, partly because of the swelling, but also because of the bradykinin here. Chemotaxis means that these chemical mediators are drawing neutrophils, monocytes to this area here, so that we have just a massive collection of white blood cells that are going to form in this area here. And here they're showing the cleanup crew here. Now our neutrophils are phagocytizing the pathogens. Here, one and done usually. The monocytes migrating there. They can kill multiple ones at the same time here. And the same chemical mediators are going to trigger the release of even more white blood cells into circulation, leading to a leukocytosis. Leukocytosis just means you have an increase in circulating white blood cell numbers, that's all. And I think, you know what, I'm going to let you guys go early here by a full 30 seconds, I think. You're welcome.
Thank you.